Okay, what's up, guys? This is 2015 question number one. This was asked for last week's free response. And okay, so this is talking about rate. I'm assuming you guys read it. I'm going to dive into um, letter A. How many cubic feet of rainwater flow into the pipe during the 8-hour time interval? Well, if my rate is 20 sine and all that good stuff, we just have to take the integration of the rate. I'm going to write A over here from 0 to 8 r of t dt, which you're going to input in your calculator, and you'll get 76.571. Okay, that's it. Letter B. All right, is the amount of water in the pipe increasing or decreasing at time t equals 3 hours? Give a reason for the answer. Okay. Okay, so on one hand, we have the rate of the water flowing into the drain pipe, which is R of t. And on the other hand, if you read the problem, you have water coming out of that drain pipe modeled by d of t. And we're trying to figure out if the water in the pipe is increasing or decreasing. So at 3 hours, if we have more water coming into the pipe versus going out, then obviously the water in the pipe is increasing. There's more water coming in versus water going out. Um, and on vice versa, not vice versa, but on the other hand, if we have the water of the pipe going out of the pipe more than the water going in the pipe, then obviously the water in the pipe is the level of the water is decreasing. So we could figure that out by finding the rate of the water going into the pipe at my third hour. And if I subtract that from the rate of the water leaving the pipe, right? And if I get a negative value, that means the water in the pipe is decreasing. Okay, because in order for you to get a negative value, this guy has to be greater. The water leaving the pipe is more than the water going into the pipe. Okay, so if this guy is greater, D3, that means there's more water leaving, which means the level of the water is decreasing. It's getting less water there. Okay, now likewise, if it's going to be positive, if you get a positive value, if I take R3 minus D3, well, that means R3 is bigger. For you to get a positive, that means there's more water going into the pipe versus water going out of the pipe. All right. Now, taking that into your calculator, you're actually going to get, I believe, negative 0.313632. Obviously, this is less than 0, right? Which means water is leaving your pipe more than it's coming in, right? And if you want to put, obviously you have to give reason for your answer. You could say, um, since R of 3 is, oh, I'm going to put, let's just put greater, no, it's not greater, less than, yeah, less than D of 3, um, the water in the pipe is decreasing. And that's all you have to say for the reason. Okay. Letter C. At the time t 0 to 8, is the amount of water in the pipe at a minimum? Okay, let's see. So essentially they're asking for what is the absolute minimum between 0 and 8. So if they're asking for the minimum amount of water, don't forget to include those endpoints. I'm talking about 0 hours and 8 hours. Okay, so to find the minimum, well, we're going to take the derivative and we set equal to 0, find my critical numbers, do the first derivative test, and figure out from there. So let's first talk about the amount of water in the pipe at a certain time t. And we started out with, I believe, 30. There's 30 gallons of water, or no, cubic feet of water in the pipe at the beginning of time, plus, now I'm going to write this next part here from 0 to whatever time. I'm not sure whatever time. This represents all my time from 0 to 8. And I have, obviously, there's going to be a difference. You have the amount of water going into the pipe, and I'm going to call it R of x, minus the amount of water leaving the pipe, d of x. And this is my dx. Now, the reason I use this t right here, since we're looking for a specific time, I'm going to use t as for that specific time. And I've changed my rates to d of x and r of x and d of x, right? Just make sure you don't have the same variable from here to here, okay? Now, if this is going to, and let me clarify again, this right here represents the amount of water in the pipe at t, given the fact that t is somewhere between 0 and 8. We're only talking about from 0 and 8, and I'm going to include beginning of time and at the very last hour 8 as well. Okay, this is simply the amount of water in the pipe at time t. Once again, you start with your initial amount, and we add whatever's been accumulated from the beginning of time to whatever time you want to find. And again, this is the water going into the pipe. This is the water going out of the pipe. Okay, so if I'm looking for the relative, or not a relative, but just a critical number, well, obviously I need to take the derivative of this whole thing. So we have derivative 30, which is 0, great. And when we take the derivative of this guy, this is the fundamental theorem of calculus. Okay, and I'm going to do a quick little review. If I take the derivative of something of this structure, you have whatever number here to, let's do, excuse me, I'm going to put a variable here, x, and then let's say you're taking the derivative of, let's not use d, oops, f of t dt. Fundamental theorem calculus says this is just going to be f of x, pure and simple. You're simply going to replace this variable with whatever this variable is, as long as you're just doing the derivative. Okay, so based on that, if I take the derivative of this guy, I'm going to put derivative modifier here. I've got 0 plus, and then derivative of this using the fundamental theorem of calculus, we just get r of t minus d of t. Okay, and you notice the little play with the variables, because we ended up with r of t minus d of t, that's given to us in the formula here, right? Or in the equation here. Here's r of t, and then here's d of t. So hopefully you already had that set up in your calculator from the previous parts. If you set this equal to 0, you're looking for where your two graphs intersect, right? And you're going to get two locations. You got 0, and you've got also 3.271658, which you should store as a letter, whatever. Okay? And so now these are possible critical numbers. 0 is already one of my endpoints, so great. I'm going to include that anyway. So you're going to create a table here. You've got the points of time that you're going to test out. Obviously, we have 0 and 8. Those are your endpoints because they're looking for an absolute minimum. And then your whatever your storing letter is, let's call this A. I'm going to put over here store A. Whatever that value is, that's going to be store A. That's in between 0 and 8. And you're going to figure out the amount of water in the pipe by substituting these time values into the equation. Okay, so if you get for amount of water at 0, well that's just 30. Nothing has happened so far. We've already started with 30. Taking the next value, the 3.2, the one you stored in for A, into this equation here, you should get a value of, let's see, approximately 27.964561. And then inputting 8 into that equation, you'll get 48.543686. Okay, so looks like clearly this guy right here is my minimum amount, right? And so they're asking for at what time t is the amount of water in the pipe the minimum. Justify your answer. This right here is kind of my justification right here. I've tested all my critical values, including my endpoints, to see what's the lowest possible number I'm going to get, right? Now your absolute minimum can only occur from these values here, critical numbers or endpoint. So I'm going to say my conclusion is the amount of water in the pipe is minimum at time equal to, and I'm going to round that 3.272 hours. Okay, so that's it for letter C. I'm going to have to go another page to go to last letter D. Okay, letter D. The pipe can hold 50 cubic feet of water before overflowing. For time greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow. So I guess we're assuming, the water going into the pipe eventually will be greater than the water coming out of the pipe, because if that doesn't happen, then the pipe will never overflow. Okay? But all they want us to do is write, not solve, an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. The pipe will begin to overflow as soon as the amount of water reaches 50. Okay, so one more time. When the amount of water equals 50, that's when it may begin to overflow. Okay, and so back onto letter C, the amount of water is simply 30. Remember the initial amount of water in the pipe before it's when time started, plus my integration from 0, and they're looking for a new letter that gives a time w for the pipe. Okay, so here's got to be w. And I still have my original equations, my r of t minus d of t dt, and we're trying to figure out when this equals to 50. That's when the time is when the water in the pipe is going to start to overflow. Okay. If you have any more questions, please come see me or hit me up on Remind. That's it for now, guys.